Thank you for the introduction, and also thanks, ATLANT 3D organizing this, fantastic conference. I'm Xichun from University of Strathclyde. This talk actually is based on recently published CRP essay. CRP is an organization called the International Academy of Production Engineering, which this essay is authored by Professor Fang, which contributed this ACSM concept, and also myself. Dr. Wei Gao from Copenhagen University contributed on the process development and the system development, and also Dr. Dai from PTB in Germany, and Professor Takaya contributed the metrology. They both contributed the metrology. So this talk actually is just give some understanding of atomic scale manufacturing from mechanical engineering point of view. So before I just take the chance to introduce my laboratory. I'm coming from a Center for Precision Manufacturing, which was established 10 years ago. We particularly focused on the mechanical process development. We focus on metal forming and the process development machine tool, and also art precision machining for machining precision optics and photonics, and digital twins, digital manufacturing, smart manufacturing. And we are moving towards atomic scale manufacturing. So within the center, I'm leading the precision engineering research group. Actually, our core expertise is coming from art precision machining. We're developing art precision diamond turning grinding process for optics, photonics, and also we do like a molecule dynamic simulation to understanding the manufacturing process, and digital twins machine tool development. But we extended our expertise to micro and nano manufacturing. We're using lasers, laser assisted machining to achieve 1 + 1 equal, a larger than 3 effect. In the field of nano manufacturing, because we're from a mechanical background, we concentrated on some mechanical based originally. For example, focused beam based machining for manufacturing plasmonics, nano gratings, and then we extended this expertise to nano electrode lithography. We're developing roll-to-plate nano electrode lithography to generate structures in the wafer levels, and also recently we developed AFM-based tape-based technology called pulse modulated local anisotropic oxidation lithography. Basically, we could, through programming the pulse and controlling the speed, we can program based on the generated nanostructure. We can program it to flexibly, quickly generate the nanostructure. So this is introduce myself and my research group. So in this talk, I will really focus on ACSM. So this is the outline. So this is the summary of the development of manufacturing technologies. The evolutions of manufacturing technology and systems can be classified into 3 manufacturing paradigms based on the skills of manufacturing precision, functional feature size, material manipulation, and the underlying theories. So manufacturing 1 is a craft manual manufacturing. The achievable precision is millimeter or sub-millimeter scales. So the manufacturing 2 is precision controllable manufacturing based on classical theory. The 4th industrial revolution took place in these manufacturing paradigms with focus on automation, standardization, and digitalizations. The achievable precision is in millimeter or nanometer scales. So manufacturing 3 is atomic control manufacturing. As a series of describing discrete energy states of items or radiation, quantum physics become the underlying theories for manufacturing 3. The achievable precision is in atomic scale or close to atomic scale. The ACSM, we call it atomic and close to atomic scale manufacturing, is a fundamental technology in manufacturing 3. It is aims not only to achieve atomic scale precision, functional feature size, such surface damage, and also to achieve material manipulations in the atomic or close to atomic scales. It is developed. It is driven by the demand to achieve atomic scale functional feature size and precision for next future generation products such as quantum chips, 2D processing 2D materials and single atom transistors. So ACSM is underlying technology. To comprehensively study ACSM, we need to address three aspects of scientific issues. The first one is fundamental mechanisms of atom manipulations and interactions, the interface between atom and also macro objects. Another is the process approach and equipment to precisely control the localized energy on the directed on the items of interest, and also a new atomic and close to atomic scale measurement technology and systems to quantify, evaluate the process. So it needed to establish a framework to address these three fundamental scientific issues through solving the scientific problems, and also propose practical solutions towards the overall objects to establish ACSM fundamental theoretical systems and the large scale and industrial viable ACSM process and measurement systems. So I will introduce the research contents one by one in the following slides. So currently, the ACSM process developments are rooted in semiconductor-based or nano manufacturing approach, but attempted to go beyond to address the quantum uncertainty problems through removal, migration, or additions of items, atomic layer or atomic cluster to realize a true ACSM capabilities. So today, in the meeting, the ALD, ALE are typical removal and addition ACSM process. STM tape-based item manipulation process is a typical migration ACSM process. It's using either vertical or horizontal or lateral mode to migrate items from one location to another to generate a new product. Fundamentally, the SPM tape-based process and also like ALD, LE, this kind of chemical self-limiting process, and also including the HDL approach, they are relies on atomic interactions to achieve ACSM capabilities. For this process, these are the dominant interactions, such as making or breaking the chemical bonds, manipulate van der Waals force, Pauli repulsions, and also electronics excitations. So energy beam-based ACSM process relies on matter-like materials interaction to realize item removal, migration, or additions. For example, SPM-based item manipulations of silicon, impurities in graphene through electron sparking is one of the energy beam-based process. For this process, these are the dominant interactions, such as photon chemical reactions, photon thermal effects, and also excitation, and so on. So these are the underlying theories. So it is challenging to develop a true ACSM processes because firstly we need to choose prepare a suitable work materials is stable and also is stable to use. And not also important to just follow on question. It needed to establish a very high fidelity and high computation efficient modeling approach and framework to address the fundamental issues. So in this case, the machine learning based interatomic potential from first principle calculations or some hybrid DFT of Monte Carlo simulation can play roles. Other challenging tasks such as developing a control approach really to achieve precision confinement of the fabrication process, not affecting the non-manufacturing zones, and also controls the beam shape is another challenge. Also packaging. So because the ATSM process currently are rooted in nano manufacturing or semiconductor based, so the current systems is kind of combinations of the systems. But in the future, should be evolutions of manufacturing systems to achieve this atomic scale resolutions. So SPM is an example, but it needs to have a larger working range. So the developing the many challenging ahead for developing ATSM machines is need a total design approach to fully meet the functional requirements, and also it may need to have a single working height of multi working height in one work platform. So this is challenging, and it needs to have low influence, low substrate damage on the product produced surface, and it needed to maybe a new innovative machine structures and new motional stage. So my researchers is working in nature-inspired new air bearings, trying to achieve even higher precision, high stabilities for a motion stage. So and also control systems, environmental control, that is challenging. So for ATSM surfaces are featured as multi-scale engineered surface. It's including atomic very ultra-fine defects introduced by the machining process, manufacturing process in the atomic structure levels, and the functional features in the micro and nano structure levels, and also the geometric features in the overall structures. Traditional approach is difficult, so some photon scattering surface metrology could play an important role. For example, some current existing surface inspection equipment such as AFM, SPM, SEM, and also some new equipment under development based on some quantum effect like the spin Hall and quantum tangling effect. These can be future ATSM equipment using a quantum probe to measure. So for example, based on spin Hall effect, by observing the transversal shift of the light reflected or transmitted from the material properties can be known. So basically, just your challenge ahead. This is some uncertainty natures of quantum physics resulted measurement uncertainties. Developing new metrology standard to quantify the metrology systems, and also the low influential measurement system in research. So last 2 slides. The last. Yeah, sorry. Yeah, so it is it's a multi-disciplinary research. I hope it needs international collaborations. And so currently, we had a journal called Non-Manufacturing Metrology to disseminate this ATSM result. And also, there are 2 conference series. It's NanoMan conference series. One will take place in Singapore, not October, it's December this year. And next year, there is a AET symposium, which I'm supporting to organize, has a topic on atomic scale manufacturing. So you're welcome to attend. And also this the new journals. I'm lead with Dimitris from EPF, and also has a topic. So you are welcome to submit a paper. Thank you.